to see that in the last lecture we were trying to figure out that what type of cost function that we can have, and then what is the problem of slope conversion with respect to a given sigma type of cost function. So today what we are going to see is that there is something, this cost function, which is going to create some problem. So we used to think about multiple cost functions. The second thing is that this cost function is not the only culprit of the slope conversion. The other thing is actually the activation functions which are also coming in between. So we will also try to figure out that different activation functions, and then we will see that typically this ReLU, and there are so many intermediate things which actually ReLU requires to be used properly. And what are the reasons behind that, why ReLU sometimes performs, sometimes it's not performing, and then we will see that what are the best practices with respect to the ReLU. And then we will see that different types of network weight initializations as well. Network weights has to be somehow initialized properly. So first I have to do So quickly we can recap that what we were trying to do is that this is actually the cost function that you have, and done. It's okay, huh? So not concentrate here. That you have some cost function, and the problem is that when we wanted to have a very simple network that we were last lecture trying to see, and the problem is that when you have a high loss, you assume that your network is going to perform or learn faster from your high losses, which was not actually happening. And the point was that when we have said that you have only single neuron like this, the weight is W, the bias is B, and input is going to be 1, and output we are expecting to be equal to 0. This is the fixed scenario. And then we have said that the initial weights are 0.6 and 0.9, and these are the weights and the biases, and the neuron output is going to be this. Everyone can compute what is this thing. You can add this thing and apply the activation over there, that is sigmoid. So this is the thing that you are getting, and accordingly this is the type of curve that you are getting, and you understand that it is going down. This is fine, and you actually have got an output of 0.09 at last. So this is the learning curve that you have. Next, what we have done is that we have changed this bias, this and this. Once just I change this bias and the weight values with the same learning rate, you are actually getting a curve like this, which essentially you can see that for good amount of time it is not going down, and after say 100 epochs, 150 epochs something, it started to get down. So the problem was that even though with the same thing initially you have got a very high loss, it was almost 1, but as the loss is high, still we are not getting learning very fast, because you can see that most of the time it was here, and after that it comes down. So what is the problem behind this thing? This is the thing that we wanted to investigate and understand this stuff carefully. And there are things that are today going to cover is going to be the some of the tips and tricks that are being used in the deep learning network when you are trying to let your network train properly. Most of the time things are not working, and then you will have to somehow understand that what is the culprit. So here the cost of, now suppose that your cost function is C, your weight vector is W, your bias is B, A is going to be the neuronal output, X is the input which is always equal to 1, and Y is the desired output 0. So what you wanted to do is that you wanted to differentiate your cost function with respect to weight, with respect to your bias, and here they are coming to be very small. Any cost function, if you differentiate with respect to your weight and things becomes small, which essentially means that loss is, which essentially means that learning is not going to happen fast, because this is the thing which is going to be coming inside your weight vectors update. So this is the whole scenario for you, and we have seen that C is equal to Y minus A, Y is the output, Y is the actual output, desired output, A is the output of this neuron, divided by 2 whole square. That is why differential can be, this 2 will be coming here, so this 2 will be eliminated. This is the A is equal to delta Z, because Z, this is X which is going in, this is the B. So what you are getting, Z is equal to Wx plus D, and Y is equal to the desired output. A is the actual output that you are getting, and Z is equal to Wx plus D. So these are the three equations. You wanted to find out the del C by del W, which has to be equal to del C by, because C is being dependent upon A is dependent upon Z, and Z is dependent upon W. So you wanted to differentiate C with respect to W. That's why C to A to Z, Z to W. It's okay. And then you differentiated them and have find out this value, and then you have seen that it's going to be, so X is always equal to be 1. So because of that, A multiplied by del dash Z. Similarly, for the other parameter, you have got the output, the derivatives like this. Now what is the problem? The problem here is that your derivative is going to come, your activation function's derivative. This is your activation function's derivative which is coming inside. So it depends upon your activation function. If your activation function's derivative saturate at some point, you understand? So suppose that your function is actually saturating. So if your function is saturating at some point, so your derivative during that period will actually be 0. So this is happening here because your function is going to be saturated this where and this place. So if your function's derivative, so what is going to be the derivative here? It's going to be very small, and because of that these things are actually going to disrupt. You understand? This is the problem last time we have seen, and most of the time these saturating activation functions which are activation functions which are saturating, this is the main problem with them. So what is the thing that one can do? Because this is the problem with your this type of MSE type of loss function. So there are two things that you can do. First is that you can change your cost function, and the second thing is that you can figure out a way to come up with another activation function. So there are both of these things are actually being done. First is that if you wanted to have a non-saturating activation function, what is that? ReLU. ReLU is a non-saturating activation function, at least in the case of this positive direction. So it can be done. So we will see that thing in our, just after this we will see that thing, that if we change activation function, what we can do. But is there a way by which I somehow get rid of this? And if it is the case that I have derivatives like this, which is not having or not dependent upon my activation functions, it will also be okay for you. So these are the two things that we are going to figure out. The first thing that we are going to see is that we wanted to play with the activation, we want to play with the cost function itself. So this is another type of cost function which says that y ln a 1 minus y ln 1 minus a. First thing is that this is cross entropy, which means that if I have a vector y, if I have got another vector a, and both of these vectors are actually binary vectors because you wanted to do some sort of classification. So what is this? This essentially take something from y and the corresponding a, and you take the log of that. So here this is going to happen y log a 1 minus y log 1 minus a. So given two vectors, you can easily find out this value. If your y is equal to 1, then this will actually be 0. If your y is equal to 0, then this will be equal to 0. So at a time when you are dealing with a single, for a vector, when you are dealing with a single element, it may be either 0 or 1. So either this will be active or that will be active. This is a cost function. Fine. So how it is coming, we will see. Why it is coming, we will somehow try to handle and see that why we have got this type of loss function. But is it a proper loss function? So yes, it is always positive. You can check. And you can also check that if y and a both are very similar to each other, then this value will actually be less, otherwise this value will actually be high. So this is actually a cost function requirement. So it's actually fulfilled. But can it handle your slow learning? Because that was one problem that you were having your slow learning. What does it mean? Then again I I differentiate with respect to this, I will be slightly fast because this will be available on internet, on your website, our website. But just you take C to A to Z, and Z to W. The same way last time we have done. So given this function, if I wanted to differentiate with respect to A, and then I wanted to differentiate A with respect to Z, which was the previous thing, the same thing. Because A is not being changed, sigmoid activation function remains to be the same. So here, if I take this thing and differentiate with respect to A, you are going to get this expression, this whole thing. Then you multiply with del A by del Z, which is here, and then you multiply with this. So del A by del Z is because that's the activation function, so the derivative of your activation function. So this is your derivative activation function. And this is going to be equal to xz. Why? Because your z was equal to summation of wi xi times the bias. So this is going to be xj for you. If you replace all of these things, again you have got this term over here. And this is the culprit who was previously also creating some problem there. You remember? This was always there. It was previously was a times delta dash z, which was going to create problem. Here also it is there. But your del dash z is actually equal to del z multiplied by 1 minus del z. Sigmoid of z. This is the derivative of sigmoid function. Yes? This is the derivative of sigmoid function. If you take a sigmoid function and differentiate, you are going to get del z multiplied by 1 minus del z. Now you replace here, and then you do some mathematics. What will happen that these things actually y delta z and y delta z will come and it cancel out, and what will happen that ultimately you have got something like this, which is like 1 by n summation a minus y, which is actually the loss that you have got multiplied by the scale. That loss got scaled with respect to your inputs x1, x2, x3 and so on. The good thing which happens over here is that your this derivative is actually getting out of the effect of your taken activation function. Is that good for you? Yes, this is the thing that you are looking for. You can sit here if you are not able to see. So this is good thing for you. So that is why our cross entropy functions are useful. But how and why, but this is not a magic by which we are actually getting. So let us see, and the same thing will happen with del C by del V, and the same thing, similar type of thing you are going to get over here. And because of that, your derivatives are no more being dependent upon your activation function when you are working using the cross entropy. Yes? Yes.
This is for like one activation function. So similarly, given that we know the number is required, we can find out such cross entropy for every activation.
No, cross entropy is fixed. You take
some other function then.
Yeah, so if you take another activation function, similar type of things are going to come. Yes. Yes. So this is, so how we have got this first of all. So this is actually small thing that I just it's going to be there, and you can use that thing. I mean you can read it from the slide. So what we are going to do is that if del C by del W is equal to this thing, you all know, which is equal to, and if I take this C, the old thing, remember that what was your original MSE function. So if I start from my MSE function and somehow show that the derivative that I am getting, I want a function. I wanted this function to be rebuilt in such a way so that the derivative that I am going to get should not be having activation terms differential coming inside. I want to avoid that. So in that way, this was the del C by del W that I was getting. Similarly, this is the del C by del B that I was getting, and this is a minus y something something, a minus y delta z, delta dash z. And then I say that I do not want this. So my assumption is that del C by del B should have to be a minus y. This thing has to be, should not be there, or should be equal to 1. I do not want this thing over here. Okay. So you can use this thing, del C by del B, which is going to be equal to a minus y. Similarly, you can say that from here what you are getting, del C by del B is equal to del C by del A coming directly over here, and this thing is delta dash z, and this thing is equal to 1 directly coming from the above things. And what I want to say is that if you take this thing carry forward here, you are getting an expression for del C by del V like this. Same thing. You just keep on substituting these values over here, the thing that we have previously done. Now the point is that I want this thing to be equal to this thing, because this is del C by del V that we are getting using this type of expression, but we want this thing should not be equal to A minus Y times this thing. We want that del C by del V should have to be equal to A minus Y only. So if I take this and equal to this is the derivation that I have said. So del C by del A times A minus 1 minus A, which I am getting from the actual thing. If this thing become equal to A minus Y, and then we do the substitution like this and then do the integration, you are going to get the same function. What we done? We have done it in this way that we have got a loss function. Then we have done the whole thing and have seen that the derivative with respect to this loss function, when we do this derivation with respect to my weights, I am getting some term which is creating a problem. Then I have said that I wanted to remove this term. So that is why I have said that it should not be A minus Y times this. It has to be A minus Y only. So if I do it like that and I wanted to say that what should have to be that C function, then I have done the integration. You are going to get this function. It's not a magic that we take cross entropy and differentiate and see that okay, in the differential activation function is not coming. We actually have removed that. So I think that you understand the main concept. Very basic integration and differentiation is actually being written. We are slightly slow, that is why I am skipping this part, and we can easily get this thing from things. So these are available on website, our course website and Moodle. Everyone is okay with this. So you understand that first thing was that with respect to cost function, problems are going to come, and what we have done, we have come up with another type of cost function, because that cost function was having some problem. This new cost function is a good cost function, and it's not having a it's not going to be getting the derivative of your activation function inside the when it got derivated with respect to the weight function. Fine. So this is one thing that we have seen. The other thing that you can say is that why don't you change your activation function? Because your activation function is saturating. Because it is saturating, its gradient is getting very small. So can you change the activation function? So yes. So from here we will start a small detour to activation functions. So this is a linear activation function for you. We all understand that linear activation functions are there, but if you have only linear activation functions inside your network, then you will not be able to. So each and every neuron will be actually having no non-linearity inside, which essentially means that having more and more layers are not going to give you better or good estimate, or you will not be able to use all the upcoming layers well. So most of the time your data is going to be non-linear. It's again fast. This is the sigmoid. So this is the non-linear activation function, the first non-linear activation function that we have talked of, and we have seen that this is having some type of problems. We just have seen that when you use MSE loss function. We have also seen that it can be a tanh activation function. The point is that if you wanted to use sigmoid, so sigmoid is going to be used when you wanted to somehow estimate the probability of particular thing, because sigmoid is always going to take you in between 0 and 1. Sometimes you wanted to find out the things that I wanted to update something, and this update can be either positive or negative. So that is and positive or negative, and the values are going to be scaled. So it may be addition of -1 or subtraction of -1, or something which is coming in between. So and during that point of time we require tanh. Then similar to this sigmoid, we have said that it's actually an activation function which got saturated. So because of that, problems are going to come. So we started to talk about this ReLU function. And ReLU function, one can say that it is not saturating. So if it is not saturating, things are fine for you. Your derivative is not going to be small, as well as your derivative here most of the time is going to be equal to 1. So we started to get these value functions coming inside. But there is something which is called as the dying value. What's the spelling of dying? D-Y-I-N-G. Dying value. So this actually what happened, we will talk about this value and why, what does it mean that it's actually dying. I think also there are two things which will happen. First is that your gradients and these gradients are going to be multiplied when you go back. And if you keep on repeatedly multiplying things, a bunch of things, and if these bunch of things they keep on multiplying, then what will happen? That if the value is more than 1, you keep on multiplying, then it explodes. If it is less than 1, then it keep on multiplying, it get reaching towards 0. So because of that, our gradients will be vanishing or exploding. ReLU is good when we talk about the vanishing gradient. It actually means seen as a solution for vanishing gradient as well. We will see that why. Yes, but if it is dying, and the reason is that it is dying because here it is saturating. This area again it is saturating. So when it is saturating, when your input to your ReLU is actually negative. Now you have got a ReLU unit and it got a negative value. So what is the derivative there? Not even small. It is 0. So because of that, what will happen? No learning. So that neuron is actually dying. You understand? When a neuron is dying, when its derivative, or you take the derivative with respect to the your weight vectors, and if it is 0, that neuron is not able to learn anything. And this is actually happening when you get a ReLU and it has got a negative value. So that is actually it's a dying ReLU. To work with this dying ReLU, they have come up with a leaky ReLU. Then they have come up with the parametric ReLU. Then exponential ReLU, randomized ReLU, and then you read in literature there are so many variants of this type of activation function. So this was the identity for you. This is the binary step function. This is the logistic soft step function. This is the tan H. This is the tan inverse. This is the ReLU. This is the parametric ReLU. Parametric ReLU says that what is going to be this thing, the slope of this, that is again a hyperparameter. You learn. And it's not a hyperparameter, it's going to be a parameter. So it's also going to be learned that by what alpha I wanted to get my ReLU to be decayed when it is negative. So that here it is also not saturated. Then exponential ReLU will say that instead of the linearity itself, yes, it is still you are decaying or whatever, but it is still a linear thing. They say that here it is linear, here it is exponential. And then there is this soft which essentially says that if I take this thing just above, it's actually shifted upwards. That's the soft plus. And the derivative is this sigmoid of soft plus. So there are so many different versions and the variants of this ReLU which are possible. And most that you understand that why softmax is why our activation functions were creating problems and why ReLU is somehow being seen and being useful for this type of thing. Then we will have to think about few more things. Everyone is okay with this. Basically, these are actually the small tricks and trick tips which has to be somehow understood. That sometimes sigmoid is working, sometimes tan H is working, sometimes ReLU is working. Why ReLU is slightly better than them, the other activation functions. Now if I say that ReLU. So its range is going to be equal to 0 to infinite. So it is not saturating. As soon as I say that it is, but you want calculating. Remember the first lecture in which I have said that the value now you have got now you got a fraction function which will take each and everything between 0 and 1, so that when whole thing is actually being normalized, thing will perform in a better way. Because within a some neuron is taking to somewhere else, some neuron is taking to things somewhere else. And suppose that this neuron has taken, one neuron has taken into some other zone because of its own weight vectors. Some neuron which has not got considerably high weight, because of that the output that it's actually giving is in the range of 1 to 10. And the other neuron is giving output which is from 5 to 100. And if you merge both of them, you are going to get problem. I think the same thing Nikhil you was also talking in the last lecture. When you have got a ReLU which is not a saturating function, then this is going to happen. It's not a saturating thing. Every output, neuron output is not going to be within a range. The things are somewhere what will happen, that some neuron will talk in terms of 1 to 10, some neuron will talk in terms of 5 to 100. And because of that, things will create some problem. Yes, so the first thing that one should have to understand is that that ReLU, when you want to apply ReLU, you will have to normalize your input. Your input is first of all going to be normalized, which essentially means that whatever the input vectors that you have, first of all convert it between 0 and 1. The second thing is that initialize your weight vectors. So your weight vectors are also going to be properly initialized, because if your weight vectors are not properly initialized, then what will happen? That some neuron will take to some other zone, some neuron is taking to things into some other zone. So that is why the weight vectors are normalized, as well as we do not want very high weight vectors. Because if your weight vectors are very high, then what will happen? Your one input will go inside a neuron, weight vector is very high, because of that you have got a very high value. At that very high value, what is that? Summation Wi xi plus the bias. This is high. Now this is going inside your activation function. And your activation function, if it is sigmoid, then it got saturated. If it is ReLU, then it got exploded. The values got exploded. So this is the problem, because of which we first of all want our network not to be having very high weights. That is why we do some type of regularization. Because activations are coming, activations can take, and they are non-linear, they used to take into some high value. And that is why we wanted to somehow control our weights. So this is one part when we talk about the regularization. But when we are going to set our weights, we usually say that whatever the weights we want to start, no, they has to be properly initialized. If they are not properly initialized, then again you are going to get the problems. And the problem that you all understand is that the values may be getting exploded. The second thing is that the gradients are most of the time multiplicative things. You all understand that why gradients are being multiplicative. Suppose that if I have x, and from this x I have got gx, then from this gx I have got f of gx. Then I wanted to differentiate f with respect to x. So then you will say that it has to be equal to del f by del g and del g by del x. Yes, but why it is got multiplied? Why it is not added? Yes? It's simple, no? This is the thing that we usually do, and this is also going to come inside your computational graph. I will talk about it. You have covered computation. We will talk about this computational graph, and then we will see that why and how all these things, partial derivative concepts, are actually embedded inside our computational graph. Well, first thing is that suppose that 1 unit variation you do here, and here you have got 2 unit variation.